What was the most important technological advance of the last century? I would argue it's in your pocket right now. It's the computer in your phone. Computers crunch billions of numbers a second to solve our problems. And some of these problems, like figuring out how to forecast the weather or figure out how diseases spread, can take our fastest computers days, weeks, or even months to solve. And we are quickly reaching the physical limit to how fast and small we can build them. So where do we go from here? We can turn to quantum physics, or the physics that governs the very small and the very precise. Using the principles of quantum physics, we could aim to develop a quantum computer which works very differently from computers of today. For example, think of the problem of figuring out how a virus would spread through your body and which cells it would infect. It's kind of like solving a maze. A traditional computer would calculate the probability of the virus taking a particular path, and then do it again for a different path. And it would do this so on and so forth until it calculated the possibilities of each path and compare them to know which is most likely. But a quantum computer sees the maze from the top down and could simultaneously figure out the probability of the virus taking all paths at once, and then know which is most likely. Just imagine with this technology how much more quickly we could find cures to diseases like HIV and even the common cold. While it sounds futuristic, we're making a lot of progress in the field of quantum computing, but several hurdles still remain, such as scalability, which means how to make the computer more powerful, and error correction, or figuring out how to correct the mistakes that the machine makes. But here at UVA, we've solved the scalability problem. By interacting lasers and certain types of crystals, we've managed to make a large number of resources out of light that a quantum computer could use. This means that our type of quantum computer would store and manipulate information in physical beams of light. So now for the problem of error correction, and a new problem, figuring out how to make the computer perform all the calculations we need. And this is where my research comes into play. It turns out that both of these problems boil down to making special types of light that are governed by quantum physics. Like this artist rendition kind of shows, we need to take the light that we have available in the lab, combine it in new ways, and figure out how to make this new type of quantum light. We've done the math. We actually know how to do this. All that remains is for us to actually make these states in the lab, characterize them, and then combine them with the resources we already have to make a realistic, scalable quantum computer out of light. Now, while this is still several years away, these types of computers offer a lot of advantages over what traditional computers can do, such as sorting through vast quantities of information to improve national security, to improve financial security, and even figuring out how diseases work so that we may better find cures to them. Quantum computing will be the next technological revolution. Thank you.